Okay, how are we going to measure pi? Well, the definition of pi is if we have a circle with some circumference c and some diameter d, pi is just the circumference of a circle divided by its diameter. Easy enough. So that's something we could in principle measure experimentally. We could map out a circle by getting a whole bunch of points some distance r, d of 2, out from the center, and then go all the way around the edge and measure the circumference and take the ratio of the two. Well, let's calculate what we'd get if we assume that this Robertson-Walker metric is correct. So we've got a circle. We can pick a circle anywhere we like because we're assuming space is uniform and isotropic. So let's pick a circle of all the points where r equals r naught. And let's vary just theta. So we'll move around in theta and we'll assume that phi is 0 throughout. We're not losing anything by making that assumption because we should get the same answer for any circle. So I have a circle of radius r naught made by varying theta all the way around with phi equals 0 and no change in delta phi. Now, how are we going to use the metric to work out how big the circle is? Well, what we need to do, this metric tells us the little bit of length corresponding to a little change in any of the coordinates. So what we have to do is take a big change in the coordinates, say going all the way around the circle or all the way across the diameter, and break it up into lots of little bits. So let's start with the circumference. We can break that up into bits corresponding to a small change, delta theta, in the angle. So this will be a small length here, delta s. And what's delta s in this case? Well, delta s squared is going to be a of t squared. Now in this case, we're just changing theta, we're not changing anything else, so that's going to be 0. This term's going to be 0, so that's just r squared d theta squared. So that tells us that the element of length, delta s, is just a of t r, which in this case is r naught, the change in the angle, which is just a small angle approximation. So that's one little bit. We then have to add up all the little bits as we go all the way around the circle. Adding up lots of small bits is known as integration in calculus, so that tells us that the circumference is going to be the sum across the entire circle, which is the integral from 0 to 2 pi radians, a of t r naught, and we change the del theta into a d theta as we take the limit of these angle bits being very small. Now, what is this integral? Well, a of t and r naught are both constants here. So this is just equal to the integral from 0 to 2 pi, take the a, and r naught outside, d theta, which is a of t r naught, just 1 times d theta, so that's just going to be theta, from 0 to 2 pi, which is just 2 pi r naught a of t. So that's about what you expect the circumference of a circle to be, 2 pi r naught, just with a of t factored in there, because the universe presumably has expanded or shrunk at some point. Okay, pretty easy. But now let's look at something a bit harder, the radius, or the diameter of the circle. Now in this case, we're moving along here, and we have some bit delta s in there, corresponding to some change in the radial coordinates r. So in this case, r is changing, but theta and phi are 0. So what that tells us is that the diameter is going to be, say twice the radius, which is going to be the integral from 0 to r naught, which is just a of t dr over the square root of 1 minus k r squared. That's a k there. And you get that just by taking this equation here, setting both of those equal to 0 and taking the square root of this and that. Now, once again, a of t is a constant, so you can take it out. So you're looking at the integral of 1 over the square root of 1 minus kr squared. Now, it turns out this is quite a tricky integral because the functional form depends on whether k is greater than or less than 0. So now what we'll do is set k equal to +1 or -1 and look at the solutions for those two cases. If k is some other positive value, it behaves like the k equals +1 case, only with different constants. Likewise, if k is negative but not -1, it's just like the -1 case but with different constants. So we'll just take k equals +1 and k equals -1. How do we do that? Well, we cheat. We look it up on an online website, or we use a computer algebra tool, and that's what I'm going to use here. So this is a free online computer algebra tool using the Sage open source computer algebra system, sagemath.com. You can use it yourself. What I've done here is I've defined a variable r, and then in this case let's take it for k equals 1, in which case this is going to be a minus sign in here. We're just integrating 1 over the square root of 1 minus r squared as a function of r. And if you press go, we find it comes out as the arc sine of r. We could also work out what the situation would be if it was a positive value. So k was -1, that means it's going to be root 1 over the square root of 1 plus r squared. And in this case, it comes out as the arc hyperbolic sine. If it was some other constant, let's say it was, I don't know, 0.003 times this, all that does is change the constant. So you get a constant here and a constant inside there. So what we found out is that the diameter is going to be 2a of t, and it's either going to be the arc sine of r0 if k equals 1, or the arc hyperbolic sine r0 if k equals -1, or different constants on these otherwise. So that's telling us that the value of pi in this universe, if you remember, pi is c over d, and c is 2 pi r0 and at, and d is this. So the 2's cancel, so pi is pi in our own universe, let's call that pi naught. A's of t's cancel, r0 over either this arc sine or the arc hyperbolic sine of r0. So pi is not a constant, but will change. How will it change? Well, let's go back to our computer algebra system. So here we've got the inverse sine, so we've got r over arc sine. Let's see what that looks like. So what it does is, we should put a pi in here. I haven't put the pi in, so it's just telling you the ratio of pi to what it should be in our own universe. And it's telling us that pi is what you'd expect as long as r is small, but as the radius of your circle gets bigger and bigger and bigger, the value of pi starts to fall. And now let's change to a k equals -1 universe. So change it to an arc hyperbolic sine there. And now if you run it, what do we get? Pi once again is what you'd expect when the universe is small, but as the radius of your circle gets bigger and bigger and bigger, the value of the pi gets larger and larger. So what we've learned is that pi is only a constant if k equals 0. If k is positive, pi is what you'd expect to be on small scales, but when you measure on larger and larger circle, it gets smaller and smaller. If k is less than 0, then it goes the other way, and pi gets larger on big scales.